we shall complete the proof of a theorem using mathematical induction. Exercise 2.10, Proof by mathematical induction. Fill in the blanks to complete the proof of the following theorems. Well, actually, we will just prove one theorem here. For every integer n that is greater than or equal to 0, 1 plus 2 squared, so on and so forth, plus 2 raised to n is equal to 2 raised to n plus 1 minus 1. So this is a finite geometric series. So how do we write that using our notation for the sigma notation? It's equal to the summation of 2 raised to I from 0 to n. And it's supposed to be equal to 2 raised to n plus 1 minus 1. So we shall begin the proof. And the proof is, the first part of the proof is the base case. We will show that the theorem or the proposition is true when n is 0. To show that the proposition is true for n is equal to 0 is enough. I mean, if we shall follow what's written in the principle of mathematical induction, but you can do it. You can go on and show that the proposition is true also when n is 1 and when is 2. It's like, because by doing that, you will see the structure of the theorem and the structure of the proof that you must write down. Okay, so let us fill in the blanks. When n is 0, okay, so the left side of your equation is going to be equal to 2 raised to 0 is 1. But is it equal to this when n is 0? Yes, it's also equal to 1. When n is equal to 1, this is going to be 1 plus 2 raised to 1. That's 3. Okay, so let us pay attention to the other side of your equation. When n is 1, this is 4 minus 1, which is also 3. How about when n is 2? What shall we put here? It should be 2 squared. And 3 plus 2 squared is 7. And looking at the other side of your equation, when n is 2, this is 2 cubed, that's 8 minus 1, it's also equal to 7. So we are done with the base case. We now go to the part on inductive hypothesis. So you will write it down. So we will proceed with the proof. What must we add to 2 raised to k? Well, it's the next term. And the next term is 2 raised to k plus 1. We now go to the second line. This is equal to blank plus 2 raised to k plus 1. What must we put here? There is a hint. Substitution. So what is this equal to? It's equal to this. So we shall use our inductive hypothesis. It's equal to 2 raised to k plus 1 minus 1. We now go to the next line. There's a blank here. Hint, commutativity. It's minus 1. Next line. Fill in the blanks. Hint, addition of similar terms. So you will add these two because they are similar terms. And we now go to the last line. There is a hint here, loss of exponents. 2 times 2 raised to k plus 1, loss of exponents is going to be 2 raised to k plus 2. K plus 2 is k plus 1 plus 1. And the reason why I show this to you so that you can see that this result matches our inductive hypothesis. We are done with the part on inductive hypothesis. We will now proceed with making the conclusion. Since P of k implies the statement is also true for k plus 1, then for all integers n greater than or equal to 0, this is true.